Hello, I'm Zhansaya, and today me and my teammate Ardak are going to be presenting our project titled Energy Efficient Synchronization Using Transfer of Knowledge. Our project is mainly research-based, and we tackle the issue of energy optimization in IoT devices. So before we start, the main principle that our whole project builds upon is that given a wireless IoT device, its energy consumption can be optimized by maximizing the time it spends sleeping and minimizing the time it spends awake, so with its radio on, waiting for a packet. In other words, we could say that we want our receiver devices to sleep more and work less. By work, here we mean having the radio on, sensing the channel, and waiting for packets. So we want them to sleep more. And with that, we can define our problem and propose solutions now. So say we have a one-to-many network of IoT devices, and in the middle, we have our master that periodically broadcasts beacons. So for example, it might be sending out one beacon every 5 seconds. And these blue devices are slave devices who receive the master beacons. The most straightforward way to design the system is to simply hard-code the radio on times and radio off times for the devices. However, IoT devices suffer from high clock drifts, and to accommodate these clock drifts, the hard-coded radio on time should be really high, and that's not really efficient if we're talking energy-wise. One existing solution was developed by previous senior students. They have used reinforcement learning so that these blue devices can learn autonomously by themselves and figure out optimal sleep times and radio on times for themselves through trial and error while receiving and missing master packets. The problem with this solution is that RL takes time. So in their experiment, it took about 150 master beacons for the slaves to converge to their optimal values. We propose that this can be solved by incorporating what we call transfer of knowledge. So when a new device joins the system, it can ask for knowledge, and the experienced devices who have already figured out their optimal sleep times, optimal radio times, they can share their knowledge. So the newly coming devices don't have to learn from scratch. And I want to emphasize that our main goal here is the energy efficiency. And our hypothesis was that if we have these devices start with already close to optimal sleep time and radio on time values that they have received from experienced neighbors, this would improve their energy efficiency because they will be sleeping more. Now I'm going to talk about the work we've done. First, we had to decide the format of our knowledge packet, and we came up with this because these are the parameters used in the RL model. Sleep time is the time device spent sleeping. Radio on time is some buffer time to accommodate for clock drift. You may have heard of the term guard time, so we're calling it radio on time here. Qtable is a table that suggests best actions for these two parameters. On high level, you can think of them like this. So sleep time says, okay, device, let's sleep for this many milliseconds. Radio on time says, okay, and let's have this many milliseconds for safety as a buffer time. And Qtable says, okay, based on what we have right now, the best thing to do next is to sleep for 2 more milliseconds in the next round. And you may have noticed that it says compressed here because we have applied Huffman compression to compress our table for more efficient transmission and to fit the payload limitations. Now I'm going to talk about how this exchange actually happens, and we've implemented this thing called knowledge exchange protocol, and you can conceptualize it in 2 stages. In stage 1, we have our global timeline here, and this slave that has been receiving the master beacons and learning for a while, it decides that it has converged to optimal values, and therefore it chooses a random round and random time slot to send its knowledge to the master. These red boxes here are the master beacons, and as you can see, the interval is constant here. So this slave chose random round 2. That means that it waited for 2 more master beacons before choosing a random slot here and sending the knowledge to master by broadcasting its knowledge. The master, after receiving the broadcast knowledge packet, received a response with its acknowledgement packet so that the slave knows that its knowledge was received by the master. In stage 2, we're considering that some time has passed now and a new slave joins the system. It first receives 2 master beacons to synchronize, which means that it has to figure out what the master beacon periodicity is so that it can choose a time slot before the next beacon to send a request packet. So it chooses a random slot and broadcasts a request. The master, after receiving the request, responds with a knowledge packet if it has knowledge available at the time of the request. So for example, let's say none of the devices have converged yet and none of them have sent their knowledge values to the master. The master's knowledge base is empty. In that case, it responds with an empty packet, and this new device also starts learning from scratch. Here you can see our experimental setup in the lab. We have our master device here, and these are our slave devices. And here's a closer look. We have our slave microcontrollers plugged into Raspberry Pi devices or desktops so that we can collect their experimental logs. Now I'm going to show you a demo of our system. So these 2 devices are slave devices. I only have one of them connected to the desktop. This will be the output of that slave device. Now I'm plugging the master device into my own laptop, and master starts sending out packets. Here you can see this one's the first packet, second packet, And it says ready to send request sent successfully. Because the slave device just joined the system, it sends out the request, but it finds out that master responds with an empty packet because the master is just plugged in, it doesn't have any knowledge in space yet. So this device says, I will start learning by myself. And I'm going to skip a little bit here. As you can see, it's receiving some packets, it's missing some packets, it says timeout there. And in real experiments, it takes around 100 or more packets for these slaves to converge. But I've hard-coded the convergence threshold as 10 for the purpose of this demo so that we don't have to wait 100 packets. And as you can see, after 10 packets, the slave is going to decide that it has converged and it has chosen a random round to send knowledge. This time it chooses random round 1. That means that after one more master beacon, after this one beacon, it's going to send its knowledge to the master. Ready to send knowledge. And here you can see this is the Q table, our sleep times, guard times, knowledge sent successfully. And now I'm going to plug the second device in. So this is going to be our newly joining receiver. Its output is shown here in this terminal. And as you can see, it received the packet. It says ready to send request sent successfully. It waits for some time, and it receives the sleep delay, guard time, and encoded table. And now it starts receiving the packets using these values. Now I'm going to talk about our results and findings. And I know that this table here is really busy, but I want you to pay attention that these are the statistics that we have compiled for the first 5 beacons. We are considering cases when there is nothing transferred, so the devices start learning from scratch with zero knowledge. Then we are considering the cases when devices receive certain parameters. For example, here the devices start with the Q table, here they start with all 3 knowledge parameters available, and here we have some master intervals. So we experimented with different master intervals to evaluate our solution. I want you to pay attention to this column specifically, because if you remember, we are trying to maximize our sleep time. These are the average sleep times for the devices, and this column here represents the changes that the system experienced as a result of starting with these knowledge values compared to the base model. So for example, these values that are positive means that the sleep time has increased this much compared to the case when the devices started with no knowledge. These negative ones means that we have some reduction in our sleep time after using these knowledge values. Now, how we interpret these findings? First, sending the Q table by itself is ineffective because we're trying to achieve higher sleep time, but here the results are just 0 milliseconds, 1 milliseconds. It's really negligible. Sending the sleep time by itself is also ineffective. As you can see here, the changes are also very small. It's negligible. But in these 4 cases, as you can see, it says 6, 5, 6. So on average, our sleep time has increased by approximately 6 milliseconds, which is actually amazing. And if you notice, all 4 of these cases involve radio on time. Here we have it by itself, and here we have it with combination with some other parameters. Radio on time means more sleep, and the best one among these ones is when we incorporate radio on time with the Q table. It yields the best results, as you can see here. This is the highest value here. And now, how we explain these results? Q table, it's trained based on the sleep times and radio on times. So if we're just sending the Q table without sleep time and radio on time, it doesn't really have much meaning. When we send the sleep time only by itself, the system is configured in a way that this sleep time sees that the radio time is not optimal, and it's going to adapt itself for the not so optimal radio on time that we have at the beginning. But in the case of the radio on time actually directly influences sleep time. So when we have an optimal radio on time, it's going to influence the sleep time, and sleep time is going to converge to optimal values faster. And of course, since Q table is trained for the radio on time and sleep times, having the Q table is going to give the best actions that the device can take further to maximize its values. So these are our findings. And so far, we have looked at reinforcement learning, we have looked at transfer learning, and then we thought, what if we try and compare these models with some machine learning models? How does the solutions that we have seen, that we have implemented, compare to machine learning models? And that's what my teammate Ardak is going to talk to you about next.
So we wanted to explore if machine learning models could help predict sleep times directly, kind of like skipping the learning process entirely and just using the pre-trained model. We chose 5 different models. Linear regression was the simplest and fastest, perfect for small devices. Gradient boosting is widely used for structured data and tends to give really good results. And we also include a random forest for its ensemble trends and 2 neural network models, LSTM, because it's good at capturing sequences, and MLP, a simple feed-forward network. To train these models, we started by parsing logs collected from our reinforcement learning experiments. Each log entry had things like delta time, RSSI, sleep time, and so on. After cleaning the data and removing unnecessary lines, we generated features like rapid values, changes between steps, and rolling averages, all of which helped the models understand patterns over time. To see what kind of input was most helpful, we split the features into 5 sets, starting from just the basics like delta and RSSI, and adding more temporal history, trends, and smooth values. We also had an all set, which combined everything. We ran each model on 5 sets and found that all feature set gave the best results pretty consistently, especially for linear regression and gradient boosting. In terms of training setup, we used data from 9 devices, 7 for training, 1 for validation, and 1 for testing. From the results table, we saw that while models like MLP and random forest had strong accuracy, they were too heavy in terms of file size or inference time. For embedded development, gradient boosting and linear regression were the best trade offs. They were very fast, accurate, and small enough to run on ESP32. Based on those results, we narrowed it down to linear regression and gradient boosting for our final deployment. Here, we only used the all feature set since it had the highest accuracy, or like our square score, for both models. One key takeaway was that temporal history features made a huge difference. Including things like previous data or RSSI really helped both models perform better. Linear regression had a smaller size and was super fast. Gradient boosting gave us the best accuracy overall while still being compact enough for real world use. So once we had the final models, we deployed them on ESP32 to see how they would actually perform. For linear regression, it was simple. We just looked at the learned weights and applied the equation directly in C++. For gradient boosting, we used a library called M2CGen, which converts a trained Python model into a C++ function that we can run on the device. We created 2 versions of gradient boosting: lightweight one with fewer trees and shallow depths, made for speed and size, and heavier one, closer to full accuracy but larger in size and slightly slower. And in this table, we can see that linear regression came really close to RL in terms of PRR, with the best balance of sleep time and reliability. Gradient boosting light had the highest sleep time and lowest radio on time, so best for energy savings, but a slightly lower PRR. And gradient boosting heavy matched reinforcement learning in terms of reliability, but consumed more energy due to longer delta time. So depending on what the system needs, whether it's accuracy, efficiency, or speed, we can pick the right version. To wrap things up, our project improves IoT synchronization in 2 ways. First, by using transfer of knowledge, we avoid having every device learn from scratch. This saves time and energy right away. And second, with pre-trained ML models, we can skip learning altogether and just predict optimal behavior instantly. This leads to faster convergence, longer sleep time for devices, and lightweight system that scales easily. We think that this can really be useful in real-world settings like smart farming, where devices may go offline or be added later, industrial networks where energy usage needs to be optimized, deep sleep sensor networks where devices wake up rarely, and disaster monitoring where quick sync after reboot is critical. And that's the machine learning part of our project. Here is a short demo showing the lightweight gradient boost model running on ESP32 device. The master broadcast beacons and slave device uses the model to predict sleep time. It starts at around 4,970 milliseconds and stabilizes at 4,991 milliseconds by the 10th packet, showing that the model converges fast just from pre-trained knowledge.